Welcome to the Technical Design and Flight Readiness Review for the team from the University of South Florida.
Here is all the members who contributed to our success for the 2023 SUAS competition. From top left clockwise, we have Ria Sarah George, Michael Edgman, George Masca, Shovan Shakya, Sean Shane, Sergio Garcia. And the folks without images for this presentation are James Day, John Komsky, Kritvi Rai, and Ariel Gutse. Here is our competition team lineup and their roles. We quickly realized that we must select a vehicle that's capable of mounting all the components we're interested in putting onto the vehicle. We dubbed this payload compatibility. Vehicles of sizes too small or too big will not be able to effectively carry the payload and perform the mission. Flight endurance, as specified by the Flight Readiness Review requirements, states that an aircraft or a quadrotor must be able to fly at least 12 miles. We also have to be able to recognize that the vehicle must be able to carry a payload for payload delivery. The vehicle must also have enough provisions to able to mount a flight controller, including the GPS mast and various antennas. In addition, the imaging system must be able to also be mounted and powered from within the system of the vehicle.
With our airframe, we purchased an off-the-shelf fixed-wing aircraft that was already tried and true and plane tested before. And because of that, we found a easy-to-operate trainer aircraft that both the autopilot and the manual pilot would be able to pilot extremely easily. And due to that off-the-shelf nature, the replacement and repairing of the aircraft is extremely easy in case of a crash or a really hard land. And with that comes the modularity of having the open-source platform with the large interior, so you can place in any sort of GPS or other electronics that would be necessary from the system.
The requirement acceptance criteria in selecting the autopilot system is very straightforward. There is a very popular framework called the ArduPilot Stack. We like that the fact that it's open source, it's affordable, somewhat affordable, and it has very capable features. And some of the features, because it's open source, we can modify to do almost for everything that we want. The selection for the imaging system is very similar to the selection of the ArduPilot framework. We want something that's somewhat open source, easy to get, affordable, and satisfy the imaging criteria. We have narrowed it down to the Raspberry Pi Cam 3, which features autofocus capabilities. We found that a lot of times when we fly, the image becomes out of focus. So we want to leverage that in this very affordable environment offered by the Raspberry Pi computing platform, especially the Raspberry Pi 4. For the communication stack, we have three different requirements. We need to be able to communicate with the flight controller. We need to be able to extract imaging information to our imaging servers. In addition to that, we want to make sure that the safety pilot is in control of the vehicle at all times. We consider of combining everything into the Ubiquiti AirMax ecosystem, but we find that perhaps it's best that we don't put all of our eggs in our basket. So these systems are very robust. They're perhaps notorious in the unmanned aerial systems community. They offer great performance, and there are a lot of documentations out there. So these systems are more or less a no-brainer choice for us to compete in this competition.
So the requirement for the payload mechanism was that it would be capable of holding the full water bottle and is capable of releasing the water bottle on command, and also capable of releasing the water bottle without affecting its trajectory, so that whenever the airplane were to approach the target and release the water bottle will not drift off target due to the payload mechanism interacting with it in any sort of way. So with these criteria, the best kind of mechanism was to custom build it using rubber bands and servos. Okay, so as you can see with the photos, the design we went for was an apprentice fixed wing plane that has enough space inside and enough power to carry all the electronics that we'll need for the flight. The autopilot is mounted in the middle there in front of the servos, and the ESC and the motor is in the front, as well as a battery underneath and a compartment below. So as you can see here, there are many different modules that go into the electronics behind the autopilot itself. All that's necessary for the manual control is just the receiver, the brushless motor and ESC, as well as the servos. But those all communicate with the Pixhawk Racer, which communicates with the Dragon Link. So we can communicate with the drone through telemetry to set up an autonomous flight, which uses data from the GPS module to follow waypoints. And all of this is used to carry around the Raspberry Pi imaging stack in combination with the Ubiquiti AirMax to communicate images from the camera underneath, which can't be seen in this image, with the ground station.
So for the camera solution for the UAS, we decided to go with a panning and tilting solution. This allows us to angle the camera in a way that can better pick up the target on the ground. Designed it as compact as possible to be able to fit behind the battery compartment on foam UAS construction. Our design intent is to cut a section out of the rear of the empennage and mount it back there and wire it up. We then intend for the data to then be sent from the camera unit to the base station for processing. And now for the airdrop solution. In order to secure the water bottle to the bottom of the aircraft, we decided to go with a simple and compact solution in the form of a rubber band and servo. So the rubber band is wound around the water bottle, and the parachute is packed under it so that it's flush under the fuselage. And then we run the rubber band around and back over the servo, which then holds it in place until it's rotated and allows us to release the payload. This allows us to have a very modular system that we can fit anywhere on the aircraft, and could even allow us to have multiple if we choose to. However, as of right now, we will have one on the aircraft. The communication system on the UAS consists of a ArduPilot system on the laptop, which is then connected to a Dragon Link telemetry receiver that uses a dipole antenna to communicate with the UAS during flight. This allows for commands to be sent to the aircraft and for telemetry to be received for successful flight and control of the aircraft. The aircraft construction consists of a apprentice STS airframe manufactured by E-flite. We chose this airframe because it was very easy to get parts for, and it was widely available. It's a popular airframe that's used by many hobbyists. It's very lightweight and modular. It consists of polypropylene foam. It's a high endurance aircraft, as was shown with our long distance flight. Bill of materials: we have a brushless motor and propeller on the front of the aircraft. It has a wing which uses rubber band mounts on 2 pegs that are connected to the main body. There's an empennage with an elevator and a rudder. The main body, which contains the electronics that we need, camera system, and the battery as well. A tricycle landing gear for takeoffs and landings. A battery bay on the bottom, which has a swiveling door, as well as that will be the location for where we place our bomb drop mechanism. Dipole antenna and GPS antennas are located on the rear, and that is the construction of the Apprentice STS for our UAS.
The autopilot system involves the ArduPilot code stack, and it provides both autonomous functions and direct control by the ground control station operator. For the most of the mission, we expect the vehicle to perform pre-planned waypoints, while the ground control station operator can inject and alter waypoints so that obstacle avoidance could be achieved. We do not believe this is manually operating the controls. Although we more or less wish that we could do this process more autonomously, there is a certain amount of limitations in what we could achieve during this development timeframe. In the next few slides, I will talk about the performance metrics and performance results of our vehicle. One of the first things I do want to talk about is we are currently in the process of refining our obstacle avoidance system. Our approach in obstacle avoidance is to have 2 1000 MHz receivers at the top and the bottom of the aircraft. We use a EMI shielding material to ensure that only one set of receiver is looking at one region, which is either above or below the vehicle at one time. This way, we can try to fit a K&N model to distinguish if an incoming vehicle is coming above or at or below our vehicle. We believe this strategy could be successful because most vehicles in the competition we suspect will have a telemetry system of some sort, and most of these telemetry systems are operating within that detectable frequency range. This approach was also very friendly to test and develop on our initially planned hexcopter approach. The hexcopter approach is also one of our alternatives. We were unable to achieve the 12-mile range requirement, thus forcing us to move towards a fixed wing approach. Before we reveal our successful performance record, we will want to talk about on the subject of safety.
And mitigations, we will employ crew resource management, or CRM. This will be in the form of us managing tasks and allocating crew members to correct tasks. This will be also achieved through checklist completion and briefing team members on active missions. We also have individual health assessments, such as the I'm Safe checklist, to ensure efficient operations among team members, as well as efficient operations by the safety pilot. Environmental factors must also be considered, as well as location restrictions, the obstacles involved, and any airspace restrictions.
We can now talk about our flight readiness result. In total, we have 4 maiden flights, or flights on platforms that we've never flown before. This includes our past approach with the hexcopter models. We believe including them does demonstrate our professionalism and also our experience in operating unmanned aerial vehicles. We are fortunate to have a perfect record in terms of not losing or nor damaging the vehicle. Now, our actual mission success rate isn't as high, but in terms of flight readiness, we believe that we are executing all of our flights professionally and with the highest care, ensuring that the vehicle would at least not pose as a hazard to ourselves. Communication performance, here we're showing the position of the aircraft reported by the telemetry system. In terms of the aircraft performance, here we see the altitude performance of the aircraft. We see that the aircraft was able to maintain a steady altitude. Otherwise, if the aircraft was unstable, this would not be possible. In the autopilot performance section, we see that the aircraft was able to pretty much spot on cross the waypoints. Obstacle avoidance performance, currently our K&N model do show a very strong confusion matrix. We are very worried about overfitting, so we will be testing our obstacle avoidance system much further with perhaps different approaches. So the overall mission testing, we so far was not able to achieve success in obstacle avoidance and bomb drop because these are programs that have yet to be polished. We are unable to achieve autonomous landing on the fixed wing platform, on the hexcopter platform. That is quite trivial, as you can see. And we are able to achieve the endurance, which is a required component of the flight readiness review, by switching to the fixed wing platform. We will now show the 3 video required as our proof of. Gentlemen, we're starting on our first flight safety video. Here, George here is our safety pilot. He will fly 1,000 feet away, come back, take off, and of course take off manually and land manually. George, do you have any questions on this mission?
No questions.
Awesome. Michael, are you ready?
Yep, we're all good.
Awesome. George, you might proceed to the mission.
Roger.
Outstanding landing. Alright, I will now proceed to disarm the vehicle. Vehicles disarmed, mission complete.
Roger. Right away. Okay, now let's do the second mission.
Gentlemen, we'll perform the second flight for our safety review. This time, the aircraft will automatically take off, climb to 50 meters, and fly at least 400 feet. Well, then George will take over to manual and come back and land manually, kind of simulating an intervention. Do you understand the mission, George?
I understand.
He's our safety pilot. Do you understand the mission, Michael?
Yes, sir.
Okay, George, you may proceed when ready. Remember, the automatic mode is to switch all the way up. Gentlemen, we are now doing the third part of our safety review, which is the long 12-mile flight. George, please weigh the aircraft and tell us how much the aircraft weighs.
Roger. The scale reads 2056 grams.
Understood. 2056 grams. Gentlemen, the mission is to fly 12 miles at a loaded weight. We must fly waypoints with a max air 25 feet, which is configured at the autopilot. I'll proceed to write the missions now. Mission is written into the autopilot. We also have to ensure that the turn radius of 150 feet, and we'll be able to stay within the mission flight boundary. We'll demonstrate that through our telemetry recording here. And angle of climb and angle of descent of at least 20 degrees. George will be manually taking control of the aircraft to take off and land. So please, George, maintain an angle of climb 20 degrees until we reach the comfortable height and switch to autopilot.
Roger.
Understood. Do you have any questions of the mission?
No questions.
Okay. And the mission is configured so that it will stay above 75 feet AGL. It's actually configured to stay up at 164 feet. So we are well above the threshold. Alright, here is the distance traveled. We can subtract 8 meters from the start. George, whenever you're ready, start the mission.
Roger. Take off.
Go ahead. Stop. I will now disarm the vehicle. Vehicle disarmed, mission complete. Overall, we feel that we are ready to showcase our developed platform where we are very excited in coming to Pax River to demonstrate what we have. And we are very thankful for the volunteers behind this competition in giving us such an opportunity, and I think we will have a lot of fun. Thank you very much for watching our presentation.